Okay, we will take up a new topic today, the doubly fed induction generators. So far you are told that the advantage of induction machine is that it is a brushless machine in general because of the squirrel cage rotor. Okay. And almost 90% of the induction machines operate mostly in squirrel cage mode. Okay. Either it is die cast rotor, aluminum die cast, now they are talking of copper die cast also, or you have a braze rotor where you can put bars in the slots and braze it at the end through end rings. Okay. So, it is a compact rotor, and that squirrel cage rotor is supposed to be a very versatile structure which makes induction machine one of the most popular one, and also it is also having minimum weight per unit power. And typical cases like wind machines, your generator must be sitting on the top of the tower. Therefore, it is always advantageous to have the equipment which is lighter. It should not be heavy, okay, because that will add to the problem of the structure which has to carry it. Now, of late there has been a relook at a doubly fed machine. After all, you know that DC machine is a doubly fed machine, a synchronous machine is a doubly fed machine. Okay. Only other variety of singly fed machines are the reluctance, switched reluctance or reluctance machines or permanent magnet machines, where the flux is produced by the magnets or permanent magnets, and therefore, there is no need for excitation. Okay. And in the two conventional machines, there is one member which carries a DC to produce the magnetic flux both in DC and synchronous machine. Okay. Now, this induction machine also can be doubly fed if you make the rotor terminals accessible, and you can make the rotor terminals accessible only in a wound rotor machine, where the rotor winding is identical to stator windings. Okay. I hope you are aware of this construction. Just like you have a stator winding wound for 3 phase P poles, rotor winding also has to be wound for 3 phase P poles. It can't be wound for any other poles. So, the advantage or the features of a squirrel cage machine is now being taken out, because the rotor has to be wound for the same number of poles as the stator in a wound rotor machine. So, wound rotor machine tend to be a little more complicated than a squirrel cage machine, because you have to start winding the rotor. Unlike in squirrel cage, you can perhaps do more manufacturing automation. So, if you wound the rotor 3 phase, so you must have the same type of open slots where you can drive the coils into them. Then you have to bring out the 6 terminals, that is 2 terminals for each phase, and then those terminals have to be then electrically short circuited or soldered to the slip rings. So, you can have a maximum, how many slip rings you need? How many slip rings you require? Huh? How many slip rings you will require in a slip ring machine? Can I have 1 slip ring? No. Can I have 2 slip rings? Huh? How many slip rings that you will require? Huh? Minimum 3, because they are 3 phase. So, in a stator also you can have minimum terminals. How many minimum terminals you can have a 3 phase machine? When you bring it to the terminal box, See, I mean you do not touch into the windings, right. Okay. You only operate through the terminal, okay. Okay. And the terminals, a terminal box will have the terminals brought out from stator and rotor. So, stator will bring out the terminals to fix to the supply, okay. Then how many minimum you should have? You must have minimum 3, even if you have star connection, then the star is also maybe not a grounded star, open star, okay. Or a delta connection, anyway you have no star point, therefore delta connect can have a minimum 3 terminal, okay. And you can have an identical connection to the rotor of a slip ring machine as a stator. So, rotor can have a minimum of 3 terminals, which means internally you must connect the 3 phases in such a way in delta and bring the 3 terminals to 3 slip rings, and those 3 slip rings should be externally connected through brushes, right. And you have, so the terminals which will come into the terminal box is actually connected to the brushes, they are not connected to the slip rings. Is it clear? Because the construction feature is first important for you to know how it works. You can have 4 slip rings also. When do you have 4 slip rings? When you have a star connected and star point is also. So, you can have 1 star pointed slip ring also, okay, right. So, you have 3 slip rings, 4 slip rings, and you can also have 6 slip rings. 6 slip rings, each phase is brought out, each phase has 2 windings, 2 terminals, and that 2 terminals are brought to 2 slip rings. So, if you go to our labs, you must have seen machines with different slip rings, if you have observed. Have you observed machines with different slip rings? You have not observed because you do not have time to observe. Okay. Okay. So, there are several machines here in our laboratories which have several slip rings, okay. And sometimes they even have more slip rings to put some search coils, etc. Some of the educational machines have more slip rings. That means, if you want to look at the waveforms, etc., you can put some search coils and bring it out, right. So, you will have this multiple slip rings, okay. Then they are brought out. So, the problem with these wound rotor machines or doubly fed machines is that you need this complicated construction of slip rings and brushes brought to the terminals, and then you do the external connection. So, you need an external connection, because if you just short circuit the terminals, then there is no advantage, because then you can as well go for a squirrel cage machine. So, you would like to have a wound rotor machine because you want to control through the rotor. You must have seen, if you connect external resistances through the rotor, it will also change your characteristics. If you increase the rotor resistance, it will shift the slip at which maximum torque will occur, right. You must have studied this in the basic. So, you will shift the slip at which maximum torque will occur, while the maximum torque will not change, right. So, varying the rotor's resistance will vary the characteristics of the machine, which is not possible in the case of squirrel cage machine, where you can't vary the resistance of the rotor unless through internal what we known as a skin effect, okay, or a displacement rotor. Next point is that you can put an external resistance through the rotor, or you can apply a voltage to the rotor, right. What is the nature of voltage you can apply to the rotor? What is the nature of voltage you would like to apply to the rotor? What nature of voltage? I hope you know what is the nature of voltage. Huh? So, you would like to apply a sinusoidal, you do not want to apply DC. Would you like to apply DC to the rotor? You can apply DC, it becomes synchronous machine, right. Okay. So, you do not want to apply DC, you do not want to apply a square wave voltage, right. So, you want to apply AC to the rotor. So, apply a voltage AC to the rotor, okay. What will happen and what frequency? Huh? you want to apply to the same frequency where the voltage is induced. So, induced voltage in the rotor is slip frequency, means if it is running at 10% speed for a 50 hertz machine, the rotor frequency must be 5 hertz, you will be applying 5 hertz voltage. So, 5 hertz voltage, 3 phase 5 hertz voltage you must be applying to those 3 terminals or 6 terminals or 4 terminals, is it clear? And so, you need to have a source which will give you that slip frequency. Okay. In fact, there was a time where this was considered to be a very sophisticated method of controlling the speed of induction motors about 30-40 years ago, and they were very much in vogue. You know, there are different variants called Kramer drive, Scherbius drive, then you have these Schrage motors and so on. They were all AC commutator motors. There is a whole book written by one Openshaw Taylor titled AC commutator motors. It is a very good book, very good old classical book. It is very cheap now, you can buy and keep it with you, right. So, that means you can control the speed through this applying the voltage to the rotor. Okay. So, the motor can operate doubly fed motion. So, you can put some power through the stator and power through the rotor also. Okay. When you start feeding power through the stator and rotor, where will the power go? Huh? You can feed P1 through stator and P through rotor. Okay. Anything happens, or you know, think of what will happen. I have put P1 through stator and P2 through rotor. Okay. If all losses neglected, if it is operating as a motor, the P1 plus P2 should get out of the shaft, isn't it? After all, you can't have, you know, you can't be just you know, pump. It is like, you know, you are putting water into a tank through two taps, you know. So, it will ultimately will rise the level, and internal water level must go out, okay, right. So, you can pump in water through you know, the power through the rotor, power through the stator, and put it together. So, you can have a doubly fed machine can have a power more than the rating of the stator power. Okay. Then when you can supply power through the rotor, you can take out power through the rotor also, by, you know, isn't it? You can take out, when you can from the supply, you can supply the power, and you can take out power and feed it to the supply also. Okay. So, you will have P1 through the stator and minus P2 through the rotor, and P1 minus P2 will get out of the shaft, right. Have you understood this? What is doubly fed means? So, you can have P1 positive or negative, P2 positive or negative, and P mechanical positive or negative. Okay. So, which would mean this doubly fed machine can work as a motor, can work as a generator, then work super synchronous, work sub synchronous. Is it clear? So, the speed can be, it is not that it will give you a 0 torque at synchronous speed. So, your whole concept of a squirrel cage induction machine, where all the power was just fed into the rotor, does not apply here. It is not valid here any longer. Okay. Now, let us look at this new paradigm today and see whether we have what we are trying to say is makes sense. Okay. Now, why are we one of the motivating factor for this has been this wind turbine, right, because I hope you have now some sensitized to what is the wind turbine, right. Wind turbine is the reverse of a fan in the simplistic terms. So, the wind blows on the blades, it rotates, okay. And you know, you must have seen some rural kids just have a paper this thing, and they just run and it rotates, because you can't afford it in the cities, because you can't run in the roads anyway. Okay. So, villagers can have this luxury of having a you know, the old class books are torn, and after they pass the class or fail the class, whatever it is, and they have they they pick up a stick from the farm, okay, maybe sugar cane or something like that, and put a small needle and they run it. Okay. So, when they pass through that, it rotates, right, and now you would like to, that is also a simple aeronautical exercise. So, if you reverse, so your there the wind has power we said, and that will rotate the blades, and which will, that power will have to be converted into electrical power, right. Now, what speed it should rotate? The turbine has a characteristics, right. So, what is the, you at each wind speed it has a characteristics, okay, and typical characteristics will be as follows, right. So, the power it will give will be something like this for for different wind speeds. This is say W1 wind speed. Okay. Now, if you say higher one W2, okay, W3, okay, and I am just drawing some approximate W4, okay. Right, and now that means for a given wind speed, for different RPM it will have different power, different rotational speed. This is the characteristic of a wind turbine. Now, for a given wind speed, what you observe is you get power is varying, and what is your objective? You must get the maximum power. If it is running at 4 meters per second, I want whatever maximum it can give. So, at this W1 it will give you P1, okay. W2 it may give you say P2, W3 it may give you P3, W4 it may give me P4, and W5 it may give me something P5 or whatever it is, okay. Huh? Wind speed and RPM has no relation. This is one of the fallacies that many people are carrying. Wind speed and the wind speed and the rotational speed has no direct relation. This is one important thing. Therefore, at each wind speed what RPM you run, so that is one which will, maybe you would like to follow some path like this. This you can call it as the maximum power locus, right. Say you are not making on no load, because load is taken out. If you go on changing the load, obviously RPM will change, okay. So, you please understand, you are talking of science and engineering out of the things, not art, okay. So, what is your objective is for every wind speed, ideally I must run at these powers, okay. Okay, so what you should do is, you know your induction generator, it has these characteristics, isn't it, okay, and you have that curve for each wind speed to give, it must operate at that speed, okay. So, it may have for the same P, let us say that I am saying that let us say P1, P2, P3, P4, you have the RPMs say N1, N2, N3, N4 as an induction generator, isn't it. For this P1, P2, P3, P4, here you have say N1 dash, N2 dash, N3 dash, N4 dash, isn't it. And so, you will notice that N1 need not be equal to N1 dash, I mean, because these are, one is a turbine characteristics, another is generator characteristics. Therefore, okay. So, your interest would be match turbine characteristics with generator characteristics. That means you would prefer to do N1 equal to N1 dash, N2 equal to N2 dash, okay, and N5 equal to N5 dash, etc. Have you understood this? So, there is always a mismatch between the turbine characteristics and the generator characteristics. Okay. Now, that means if you operate at a near fixed speed, induction generator operates at near fixed speed. So, if you look at the actual characteristic of a generator, see this is the characteristic. So, your range of speed or slip is narrow. Say from no load to full load, it is a very small slip. Now, same in the case of motor. A motor is also a near constant speed motor, a generator is also a near constant speed because you maintain the rotor resistance low, right. You can make it a highly variable, I can always make it, but where rotor resistance is high. Do you prefer this? Do you prefer this? Would you prefer this characteristic or this characteristics? Low rotor resistance. Why? You do not want the rotor get heated. So, all your wind energy should not just to get the rotor heated. Okay. You want to have a low rotor resistance, low losses, high efficiency, right. But then if you have a very narrow speed range, where the turbine requires a wider speed range. Therefore, the present trend is variable speed wind machines. So, this is our required. So, we go for this is one of the things we can achieve through doubly fed induction generator. This is one of the very recent, I would say last 5 years or so developments, okay. And some of the company like GE have some patents on this, etc. And this is one of the helping hand has come from helping hand for variable speed prime movers has come from power electronics, because why? It is due to the development of converter, inverter technologies. Because you can get from AC to DC to AC. This is what you can do, right. That would mean that you can go for some frequency F to frequency SF to frequency F, right, or that means frequency F to DC to SF to DC to A, right. So, you can either way you can do, that means from supply frequency F to slip frequency SF, or so slip frequency SF to supply frequency F through a DC mode, okay. So, you can have from the machine you have SF, okay, then you can have DC, and then you can have F to the grid. This is the rotor. Is it clear? So, this is one converter here, this is a one converter. So, one is the machine end converter here, which is on the rotor side, and other is the supply end converter here, okay. So, from SF to S, this will be a rectifier, okay, and the power flow can be done, power can flow here, right, or power can flow here, is not it. So, I can feed power through the rotor or take out power from the rotor through the grid, okay. Any doubt on this? Okay. So, let us we now think of an arrangement where this this conversion thing is possible. Okay. And this has become a very versatile international project today. Okay. When they have 4-5 megawatt, we are looking at 4-5 megawatt single unit, and the power handled by this may be even 30% of this. So, you can see 30% of 4 megawatts or 3, even 3 megawatts will be this rotor will have to have at least about 1 megawatt. Rotor must carry 1 megawatt. Okay. So, that is the range we are talking about today. Okay. Now, power versus wind characteristics. So, your wind blows, right, at very low winds you do not want your machine to run, is not it? Then it will be uneconomical, right. So, there is what is known as a cut in speed. Low wind speed, okay, and there is also a there is also a speed we call it cutout speed. Why? Why do you want to cut out speed, a maximum speed? Why are you so much bothered? You have increased power, what is there? So, typically the cut in speed means it almost does not produce much power. Okay. So, you will find, okay, it may go something like this. So, this is the sort of a maximum power, okay, it may go. This is the sort of a cut in speed and cut out speed. Beyond which why they do not want to go is, this is called gusting. If you operate at very high wind speed, it may damage the equipment because of structural problems, etc. It is not only electrical, right. So, you would rather do not produce, there may be vibrations and various things. Okay. So, this is called gusting. So, this is the power versus wind characteristics, right. So, as I told you that you must try to have at each wind speed the suitable power, okay, and that means suitable RPM. Okay. So, as I said, this is W1, P1 should correspond to some N1, and this may be W max, this is P max, which should be corresponding to whatever is the N max. So, you in this whole range you require. So, the wind machine developments have been over the years undergone considerable R&D efforts. Sometimes they say, why do not you use two machines? That means you have one small machine when you have a low power, and you have a big machine when you have big power, right. Supposing this is 1 megawatt, this may be about 200 megawatt or 200 kilowatt. So, you may have two machines, one operated low speed, another operated high speed, wind speed. So, these are some of the practical aspects of the wind systems. Okay. So, the question is match the turbine and generator characteristics. Cage induction generator has limitations of speed, so you go for doubly fed induction generator because of better control on speed. Clear? Okay. So, typically you have the doubly fed machine as follows. You have the grid, okay, you feed power, right, PE to the machine, okay, then you take out some rotor copper loss, okay, then it has a goes to the air gap and we call PG, no problem, PG. Then you have, let us say you have rotor, you take out some power PR, right, and this will be at an FR which will be, which we also call it as S times F, where S is the slip, if this is the frequency F, right. Then you have a converter which is a bidirectional, it will convert through the DC mode to F, okay, and this power is now because they may be having a voltage mismatch. So, you have a transformer and you feed it to the grid, right. Under this condition, whatever P will become Pm plus Pr. What is Pm? Is the power which is taken out through the shaft, okay. And from Pg you have a stator copper loss, core loss also may be there, and then from Pg you have the rotor copper loss, because it is cut out is the rotor side, and Pg minus P rotor copper loss will be going for taking out. In normal squirrel cage, what is PR? What is normal squirrel cage means? What is PR? PR is 0, isn't it? So, PR is 0 in squirrel cage, isn't it? Why PR is non-zero here? Because you are able to apply a voltage. So, you apply a voltage in such a direction, either has to feed a current or take out a current, and it will become a positive power or a negative power at the rotor terminals. Okay. Any doubt on this? I am just taking from basics. I think I am not till now no complicated concepts are forced on you. Is it okay? Right. Now, doubly fed induction machine, you can write an equivalent circuit. Can you write an equivalent circuit? Right? You can, I hope you know now, write an equivalent circuit of induction machines. Okay? So, you have a voltage. Okay. No problem with the grid voltage, we have a Vs is the supply voltage per phase. Please write. Then what do you have now next? Huh? So, you have a resistance. I think even in your sleep you should be able to say this, at least now you have been pushed so much of induction machine theory, okay, Rs. So, state then anything else? J times XLS. What is XLS? Stator leakage reactance, because certain flux leaks. Okay. Then what you do? Okay. Then you normally what you do is you have a stator to rotor transformation normally, okay, and you say this is, I do not know, you call it as Vg or whatever it is, and in the rotor it will have S times Vg, isn't it, as it is, even if you consider the refer to stator turns. I am taking refer to stator turns, S times Vg will be there. So, it will be 1:S is the ratio. If 100 volts is induced here, a rotor will have S times 100 volts induced. Okay. Then what do you go from here? What do you do? This is at frequency f. What will be the frequency here? The rotor circuit is of SF frequency. So, what will be the reactance? JSXLR, where it is referred to stator turns, but not referred to stator frequency. Okay. Right. Then RR. Okay. Then close it. So, if I apply a voltage here, so I will say I applied a voltage here of, let us say, Ej. Okay. Is it clear? Now, the same thing okay, I refer this to stator referred. I refer to stator referred means all at f frequency. Okay. So, what you do, you refer to stator frequency means you divide by S, the rotor. So, you have a VG or ES or whatever you may say, sometimes you call it as ES also. Okay. What will be this? This will be EJ by S. Okay. Now, you can imagine IR can be depending upon the direction of the rotor current, it can even be feeding into EJ or taking out of EJ. So, the power output may be controllable here. Okay. So, the rotary equations, you can write the rotary equation now. Okay. SVG minus IR into RR plus JSXLR minus EJ is 0. Okay. If you look at, it is a KCL, okay, or sorry, KVL. Great. Rotor loop you write, no problem, right, because I want you to understand with at this point very clearly. Okay. So, which means SVG is equal to IR into RR plus JSXLR plus EJ, am I right? Just to rewrite the whole thing, or SVG minus EJ is IR into RR plus JSXLR, and EJ refers to stator turns, that is important. EJ is referred to stator turns like a transformer turns. Any doubt on this? Whatever apply, see, if you apply rotor 100 volts does not mean EJ will be 100 volts, that you have to refer to stator turns, because your equivalent circuit is all referred to stator turns. Okay. Now, you resolve this along the IR axis, you can write down the phasor diagram, sorry, I think this, okay, this is important, phasor diagram with injected EMF. Okay. Now, this is SVG, right, and then you are injecting EJ. What does the equation says? SVG minus EJ, isn't it? I have applied an arbitrary axis, sorry, EJ have applied, and EJ can be with reference has be some angle beta. I can apply any, it is not in phase. So, with reference to SVG you apply EJ and you subtract that, okay, and then what you have, that will be the resultant loop impedance drop, which will be IR into, this will be IR into RR, and this will be IR into leakage reactance. Is it okay? You just see that this thing. So, IR into RR SJSXLR, right. So, there is an angle phi r which is between, if you say between SVG and IR maybe, that means with reference to the air gap voltage there is a phase angle phi r, and beta is the angle between VG and EJ. Okay. This is angle between VG and IR. Okay. So, you resolve all along the IR axis. Okay. This is IR, all the quantities you take IR axis, what do you have? SVG cos phi r, right. SVG cos phi r will be IR RR plus EJ cos beta r plus phi r plus beta r. Okay. This angle is beta, is it okay? You take because since the circuit will be like this, along this you can resolve all of the voltages, and then R SVG IR cos phi r, SVG IR cos phi r will be IR square RR plus IR EJ cos phi r plus beta, right. I manipulated the equation, nothing more, from the same voltage, this thing, all steady state phasor. On a 3-phase basis, PG, what is PG? Is 3 times VG IR cos phi r, is not it? PG, the air gap voltage, will be 3 times the VG into IR cos phi r, and the rotor copper loss is 3 times IR square RR, and PR is the power fed to the converter, because it is a converter, which will be 3 times IR into EJ cos phi r plus beta. Okay. So, whatever power which is getting into the air gap, these are the quantities that you have from the phasor diagram. Okay. So, what will be air gap power? Air gap power is equal to rotor copper loss plus power fed to converter plus mechanical power, that will be air gap power. What will be air gap power? Mechanical power, okay, the direction may change, but assuming that you are feeding mechanical power, that will be the air gap power. Okay. Or air gap power minus rotor copper loss will be the equal to the power fed going out to the converter plus power going out to the shaft. Okay. Right. Now, okay, now let us see how this power get distributed, right. So, one mode is, we call it as subsynchronous mode, subsynchronous motoring, okay, as in a normal squirrel cage machine, subsynchronous motoring, this phase 1, mode 1. So, that means slip is from 0 to 1 and slip is positive. Okay. In this condition, what will happen? Your PG is positive, because I have considered the PG getting out into the rotor as positive. PM is positive, because PM is what is going out of the shaft to the load, which is positive. PE is positive, because PE I had taken as the power coming from the grid into the machine, that is positive, and PR is positive, because in this case power to going out to the converter, from the rotor it is going out to the converter. Okay. And therefore, the PM, which is the mechanical power to the load, will be 1 minus S times PG. This equation holds good, 1 minus S times PG, because S times PG is the one gets into the other side, is positive. If you neglect this, supposing for the moment I neglect the stator and rotor copper losses, and so 1 minus S times PG, so S times PG will be PR. Okay. Right. Now, let us take an example. Take an example. Now, S is plus 0.2, S is plus 0.2, let us say air gap power is 100, air gap 100 units, what will PM will be 1 minus S times PG, is not it? Agreed? Then PR is, rotor is S times PG getting out of the converter, getting out of the rotor into the converter. Okay. Then electrical power is coming from the stator into the air gap, neglected stator copper loss, core loss, etc. This is same as PG. Because my PG is this. So, power drawn from the grid, how much power is drawn from the grid? 80. Why? 20 you are feeding back, you are taken 100 units from the into the machine and you are feeding back from the slip ring back to the grid. So, grid only gives you 80 units. Okay. Okay, now S equal to 0.2 you have grid 80 units, PE 100 units, these are frequency F, and PG 100 units, and PM is 80 units. Okay. Then rotor is a 20 units, and this will be 20 units here. I think it is simple. Okay. And this is at F, this will be FR is S times 0.2 times F. Okay. So, F is 50 means from 0.2 times from 10 hertz to 50 hertz you have to do this conversion. Now, you say S is minus 2. Okay. I am just taking another example, S is minus 2. Okay. Then PG becomes same 100, PM is 120. S is minus 2 and PR is minus 20. Okay. S is minus 2 means it is running at 20% more speed, right. Actual speed is 1.2 times this, right, and electrical power input is 100, power is fed to the motor, okay, and power drawn from the grid is 120. Is it motoring or generating? Huh? Is it motoring or generating? This is motoring, but S is minus 2 and you are all told earlier super synchronous etc. become generating, and that is generating only in a squirrel cage machine, not in. So, you can have a doubly fed machine operate motoring beyond the synchronous speed, is not it. So, what you find is at 20% more 120 this thing. So, from both of them what you observe, say at 0.8 speed the input power is 0.8, 1.2 speed input power is, this is the grid power 1.2 or peak grid. Okay. So, it will go on taking more power and do it. Okay. So, motoring at minus 0.2 is another curve, 100 here, minus 20 here, then again minus 20 here. Okay. Actually power is fed from here and 100 here. Okay. The grid is giving 120, okay, and mechanical power is 120, right. No, just finish it, just 5 minutes. Okay. Now, the same thing mode 3 is subsynchronous generating. So, you have S is positive, then all are negative, you reverse the direction of everything. Okay. Now, PM is 1 minus S PG is negative and PM is less than PG. Okay. I am generating subsynchronous, everything reversed. Okay. I am feeding power from this. Okay. So, let us take for example S is plus 2 generating, PG is minus 100 reversed, PM is minus 80, right, PR is minus 20, PE is minus 100 and power is fed to the grid. How much? Power fed to the grid is 80 units. Okay. Power fed to the grid is 80 units, right. So, generating at plus 0.2 means it is subsynchronous generating. So, you have grid has taken 80 units, sorry, and then it has minus 100 here, okay. Then PE has taken minus 20, okay, and PM has taken minus 80, right. So, there is a motoring is in this direction, generating is in this direction, okay. So, you can have super synchronous generating where slip is negative. So, there PG, PM, PE are negative, but PR is positive, right. PR is positive, okay. Then PM is 1 minus S PG, which is negative, and PM is more than PG. So, a windmill, a wind machine which have to give you at super synchronous the mechanical power which is more than the air gap power, okay. And then remaining power has to be fed through the converter, right. And so, S is minus 0.2, minus 100, minus 120, this is plus 20, power drawn from the rotor and fed to the grid, plus 20 means power is fed to the grid at super synchronous. So, PE is minus 100, power is fed to the grid, and P grid is 120, okay. So, this is the scenario in S is minus 0.2 at super synchronous generating, grid is minus 120 you are feeding. So, 100 is coming from this is minus 100 is going. So, the wind turbine is giving 120, okay, and out of which it is 20 it is giving to the converter out of 120 and 100 to the grid, right. Through this it is going. That means you are able to run at whatever speed. So, you are going to have a variable speed prime mover by controlling this power through these converters. How much power you can control, this is the main issue, okay. So, lastly you can draw a power versus slip at motoring, okay. So, you find that when the slip is 0, this is the if you say PG is fixed, this is PM and this is PR, okay. Now, at super sync, now you will see at super synchronous PM has become more than PG, at sub synchronous PM becomes less than PG, right, and this is the remaining PM, PG minus PM will be PR, which is the converter power, right. So, you can have this for the motoring condition, okay. Is it clear? With just a simple formula neglecting, and you can also have power versus slip at generating for the fixed gap power at subsynchronous. Out of this is the power coming from the turbine and this is the power of the converter or through the rotor, and if it is super synchronous this will become like this, because this is minus and this will become plus, right, because this is this is PM, okay, and this will become PR, right, and this whole thing is this is the PG. So, you can have a simple power sharing in motoring and generating, okay. So, we conclude that a doubly fed machine is a versatile controller mainly for wind systems. Of course, it can be used for other things also, it can be used for steam turbines, it can be used for hydro also, where you can control this is the final picture, motor subsynchronous positive positive positive, motor super synchronous, these two are positive and PR is negative, generator subsynchronous this is minus minus minus, generator super synchronous minus minus plus, okay. So, this table is very simple to give. So, I hope you have understood this, and development of controller etc. becomes more involved, because so people talk of vector control, maximum power, transient response and various things, but this is a very virgin area where lot of research is going on. I thought it is therefore necessary for you to be told about this topic as one of the special electromechanical systems. Okay, we will close it here at this.